All right, so we're back. Before we continue, a quick correction or two. Okay, I'm getting a little bit stir crazy here. That was actually 5.1 on the first page, and that made that 8.9. That was actually visible on the calculator, and I wrote 5.5 instead of 5.05. And you know, it's actually 8.9. Okay, moving through real quick. Also, when we did the Henderson-Hasselbalch, guess it's trickier than I thought, right? Down here, minus times a plus is a minus. Okay, then you rearrange that and you get the classic equation we used on the next page. Okay, so pretty much all there now. All right. Okay. All I need really is a nice cup of tea, and then I'll feel much better. Okay. So here's my nice cup of tea. Let's show you that. Okay. And today's video is sponsored by PG Tips. That's a joke. All right. Oh man. Okay, now, so back to where we were. All right, so we're talking about half equivalence. Now I just want to formalize that for you guys, all right? So half equivalence, okay, let's talk about it. So when you do a titration, when you've got equal numbers of acid and base, moles, stoichiometrically equivalent, you see, you know, traditionally a color change. We call that the equivalence point. So when moles of acid equals moles of base, we got the equivalence point. You know, that's when we see a change of color in a standard titration. Okay, so they're equal numbers. Okay, so at full equivalence, equal numbers of acid and base. So therefore, at half equivalence, if you're adding base to acid, say, you've added enough base to get rid of half of the acid. Okay, you've used up half original material. So, okay, so if you've used up half, you've got half left. If I put that in terms of a quick equation, okay, so I have HA in equilibrium with H plus and A minus. If you start removing the H plus by adding OH minus, okay, initially you got 100 here. You do it until you move 50 over, and you got 0 of these still, but you got still in equilibrium, of course. You now got 50 of those. These keep continually being removed, right? Okay, so 50 and 50, equal amounts, half equivalence. Bottom line is equal amounts of A minus and HA. Okay, so you got equal amounts of A minus and HA after you've added half enough titrant to get rid of half of the amount of stuff you're titrating. All right, so if we look at the Henderson-Hasselbalch equation, pH is pKa plus log A minus over HA. Because these are equal numbers at half equivalence, okay, so what happens at half equivalence, 50 and 50, whatever it is, that tends to 1, so log of 1 is 0. Okay, so therefore pH equals pKa plus log 1, which equals pKa plus 0, therefore pH equals pKa at half equivalence. Okay, so halfway along that buffer region is when you've added half the amount to get rid of all the material, so pH equals pKa, if you remember that slide from before. Okay, so that's a little bit more detail on that. Now, let's do a true kind of biochemist's kind of dream question, right? So, in your blood, you have a buffer, and in all, pretty much all kind of mammalian systems, it's the same buffer, okay? It's the carbonate buffer, or I should say, to be specific, the hydrogen carbonate buffer, all right? Now, blood has a regulated or pH-controlled buffer of 7.4, okay? So the buffer that does that is the carbonic acid hydrogen carbonate buffer, okay? So that's the buffer in your blood, okay? That controls the pH in your body, essentially, okay? So let's read this question. This group works. If you want to pause it and try it, give it a shot. It's kind of a harder question because it's designed for group work, okay? So if you can solve this one, you're in real good shape, all right? But let's let's go through it. Let's read the question. So if the carbonic acid has a concentration of 0.0012, and these are actual real numbers, okay? That's the concentration of carbonic acid in your blood. What is the hydrogen carbonate concentration in blood? Given that the Ka for the system is 4.3 times 10 to the minus 7. Then we can kind of look at the ratio of these two things and say, hey, what's blood better at resisting H plus or OH minus? Okay, so we're also given this information up here. The pH of blood is slightly different at body temperature. I think it's 7.1 or something. It's just that this is kind of standard temperature. Okay, so we have, well, we're going to use the Henderson-Hasselbalch equation, right? So we need pH, pKa. You could do a grid too, right? But Henderson-Hasselbalch for buffers is usually the best method. Okay. All right. So pH, pKa, and dissociated acid and conjugate base. All right. So pH is in the question, 7.4. pKa, well, it's kind of in the question. Ka is given, so pKa is minus log of 4.3 times 10 minus 7, which equals 6.4. HA tells us right there, 0.0012. And we got to figure out the conjugate base concentration. So it's kind of a weird question. It's kind of a backwards question, if that makes any sense. Okay. There's a lot of work here, so I kind of divide the page into two, kind of in my head, and we'll get going on it. So, Henderson-Hasselbalch, pH equals pKa plus log A minus over HA. Careful, because I corrected that sign, right? When we move things around, it's actually a plus, right? So that's the correct version of the equation when pH is the subject. All right. Put in what we've got. I like to kind of put things in as we get them, right? So pH 7.4. You can do like a true algebra thing and put numbers at the end if you want. pKa 6.4 plus log A minus is what we want over HA, right? We'll deal with that in a minute. Okay, we'll put that number in a minute. Okay, therefore 7.4 minus 6.4 equals log of A minus over HA. You'll see why I didn't address this yet in a moment. Okay, 1.0 equals log, make sure you can see, A minus over HA. Now I'll take it back up here, right? Okay. Therefore, 1.0 equals, I can do that whole thing where, hey, divide logs is log subtracted, right? Okay, so therefore, log of two things divided is the log of this minus the log of that. Minus log HA. Fair enough. Therefore, (1.0) equals log A minus minus the log of 0.0012. 1.0 equals log of A minus minus 0.0012 log, 0.012 log minus 2.92. Okay, rearrange it. This is our destination, so log A minus, just bring this over, equals 1.0 plus, make sure I do this right. No, that's a minus. Make sure I get my signs right. Okay, so that turns that into a plus 2. Let me get it straight. So the log of 0.0012 is minus 2.92, and I'm subtracting, and minus times a minus is a plus. Okay, 1.0 equals log A minus plus 2.92. Therefore, log A, sorry, let me just recap. A minus times a minus is a plus. 1 equals log A minus plus 2.92. Minus times a minus is a plus. 1.0 minus 2.92, which equals minus 1.92. Okay, therefore, log A minus equals 1.92 negative. Do the 10 thing. A minus equals 10 to the minus 1.92, 0.012 molar. Ah, interesting. So that's the final answer. The concentration of the conjugate is 0.012. The concentration, I'm going to write it over here, 0.012. So that's times 10 bigger than the concentration of the acid. Now, if you think about it, when you add acid to this equilibrium, okay, from an external source, it goes that way. So the more hydrogen carbonate in the tank, the better it is at resisting changes in adding H+, okay, which makes total sense. If I go the other way and add OH-, I'm removing H+, right? Okay, let me just go over that again. Let me just go, I got it wrong, didn't I? Okay, we'll go over that again. So, if I'm adding H+, the equilibrium is going to shift that way, right? Okay, because I'm going to use this to get rid of that. Okay, so in that case, if I have a large amount of conjugate base, I'm going to be better at resisting changes in adding H+. All right, let's give it the glass half full, glass half empty argument. If I add OH-, I'm going to remove H+, and we'll go that way. Okay, so I have large amounts, so this will be preferable. So if I'm adding OH to my buffer, I need large amounts of acid. If I'm adding H+, I need large amounts of conjugate base. What do we have more of? Conjugate base. So it's better at resisting changes in H+. Okay, which makes total sense because most of the nasty things out there in nature that sting you inject you with H+. So our blood is designed to resist changes in adding H+. All right. So again, this is going to be, available in the note packet, which I'll add as a downloadable PDF. Okay, so take a look at that in your own time. Now, more about drugs. All right, now, if you remember, we've talked about two different kinds of acid. There's the standard Arrhenius, right? And that's true for all acids and bases. So every kind of acid and base truly is an Arrhenius, which is just basically it increases the H+ if it's an acid and increases OH- if it's a base. Increases those ions in solution, okay? Then we had Bronsted-Lowry. Bronsted-Lowry are proton donors, which are acids, and proton acceptors, which are bases. So that's the proton transfer model, okay? But think about the glass half empty, glass half full thing. If I'm thinking about something simple like water, all right, we can go with a pseudo, well, it's not a pseudo, it's actual Lewis structure, right? So if I'm donating an H+ from, say, HCl, it comes and sticks on here, doesn't it, right? And that thing makes the hydronium ion, okay? So the hydronium ion is made through water accepting a proton. It's a Bronsted-Lowry base, it accepts a proton. But if you want to think about glass half empty, glass half full, if you look here, oxygen, if you like, has donated a lone pair to that proton, right? So this oxygen is a hydrogen plus ion acceptor, or if you like, a lone pair donor. So glass half empty, glass half full. That's the Lewis model. The Lewis model concentrates on the behavior of the lone pairs, okay, which is great when we think about certain molecules which act as technically Lewis acids and bases, even though there's no H+ involved a lot of time, okay? So Lewis acid are lone pair acceptors, and the Lewis base, remember this is a base, is a lone pair donor. Okay, so when the hydrogen comes along, think of this as donating lone pair. It's a base. Okay, so it's kind of the same idea as you saw before with proton transfer, but just viewed from a different point of view. Okay, so there's ammonia, for example. So let's do NH3. So NH3, anything with a lone pair will do this, and all those interesting drugs out there have lone pairs, right? Okay, so here we have water and ammonia. Okay, we turn into NH4. So this will jump on here. So we get NH4. What lone pair there maybe? Plus OH minus. There we go. All right. Question, kind of mentioned it already. Why do we worry about this even? It's the same thing as once said Larry, right? Just from a different point of view. Hey, you know, proton donor, lone pair donor, what's the difference, right? Well, as I mentioned, it turns out that most interesting molecules have nitrogen, right? Nitrogen has lone pairs, so they have this Lewis base behavior, right? So think of a Lewis base of anything with ammonia, sorry, anything with nitrogen, which will have a lone pair. That has some interesting chemistry. All right. Now, we are going to talk about drugs of all different kinds here. Okay. Now, when we talk about drugs as chemists, we're doing it from a strictly kind of academic perspective. It's a bit like a trip to the restricted area of the library in Harry Potter, right? Okay. No one here is Tom Riddle. We're not going there for a bad reason. We're going there for, like Harry did, for an academic reason. Okay, the nerd in me says, you know, why? Because he just goes up there with his, you know, with his invisible cloak and gets in, right? Avoids the guy with the cat, right? And so my question is, why don't they just put a lock on the restricted area? Because he just walks in. And then I think to myself, oh, but Hermione, she can pick locks with her magic spell. And then I think to myself, well, why don't they just put an enchantment on the lock? I'm just such a nerd. Anyway, so this is the restricted area of the library. We're going to talk about legal drugs and illegal drugs, but the bottom line is they're all just interesting molecules to us chemists. So we are going to visit the restricted area of the library for academic reasons. Okay, now when we think about that, back in the 1980s, there was this kind of legendary nightclub in New York. I think it was called Studio 52 or something. And everybody at this nightclub was doing like drugs in the bathroom. It was just this notorious place. And when you look back in the 80s and the early 90s, and you talk about people who were basically doing cocaine in the bathroom and heroin and things like that, they talked about freebasing. So that's a verb, to freebase, right? What the heck are they talking about? What's a freebase? Well, that's actually the pure molecule. The pure molecule has nitrogens on it, which are Lewis bases. Okay, so the free base is just the pure molecule, essentially, right? So it turns out that free bases are volatile and they tend to fall apart very easily. They decompose. So, you know, they do all these kind of weird and wonderful things to get them into their bodies, right? Back in the day, right? And that's where the term free basing came from. All right. Now, it turns out these days we have the power of science. And to be honest, you can turn these old school opiates and things like that into much more potent drugs by turning them into acid salts. Okay, so the bottom line is most free bases are volatile and not soluble in water. That's the key thing. Remember we talked about solubility. If you can make a drug soluble, you can take it as a tablet. You can't take cocaine or heroin as a tablet, right? You see these shows where they're snorting it and they're chasing dragons, all that business. Again, restricted area of the library, right? Okay. So these are not, in the pure form, cocaine and heroin cannot be ingested, right? They have to be somehow get into your body in a different way, okay? So because they don't dissolve in water, you just can't eat them. You can't take them as like oral medication. So to do that, how do you turn a free base into an oral medication? How do you make it soluble? Well, this is how we do it. We turn it into what's called an acid salt, okay? And this is really the foundation, and I'm going to go off on a bit of a rant over the next page or two. This is the foundation of the opioid crisis. What do? You take a drug like heroin, you modify its structure slightly, and it becomes 100 times more potent. You call that stuff fentanyl, all right? And then you take that fentanyl and you turn it into a shelf-stable salt which can be taken orally, and then you have an opioid crisis, right? Big Pharma, thank you so much. Now, so here we go. What is an acid salt? Okay, an acid salt, there's your drug of choice. It can be cocaine, it can be heroin, it can be fentanyl, whatever it is, right? Because it's got a lone pair on it, you react that with HCl, hence acid salt. This H plus will just jump on this lone pair and make an ion. It will stick to the other ion to make a salt. All salts dissolve in water pretty much, so that's soluble. You can now take that as an oral medication, okay? And that's the origin of the opioid crisis, right? I shouldn't really say that exclusively, because pretty much all drugs are available as acid salts because they're stable, they can dissolve in water, so you can take them as tablets, right? So there's a couple of other classics. You name it, you've probably ingested it as an acid salt, right? So here's Levitra, which is an erectile dysfunction medication. I'm not being sponsored to say that. That's a joke, okay? All right, so that's an erectile dysfunction medication, and they have the drug name with HCl written on the back, so that tells you it's soluble in water, all right? That's a legal drug, right? Maybe you heard of crack cocaine, the epidemic of crack cocaine in the 80s and 90s, right? People talk about baking it, right? So you take sodium hydrogen carbonate, and, you know, academic reason only, right? Let's go back over here first. So how do I make Levitra? So here's my Levitra molecule with its lone pair. I take my HCl, that jumps on, turns into Levitra H plus, Cl minus, that's a salt. So that's now an oral medication. Crack cocaine, they say it's instantly addictive. I don't know. Hopefully you never have to interact with this stuff. But there's cocaine, okay? And you bake it in your kitchen with baking powder. It's just so easy to make. It's, you know, restricted area of the library. Turns into, you make a mixed salt, right? So you make this guy here, which is plus, and then the sodium carbonate. It might be the other way around, but there it is. It's a minus sign. Okay, so that's called a rock. That's a rock. It's a crystalline material that's soluble in water. Right. Okay. So, you know, people that smoke crack, they're basically vaporizing it, and then when it gets into your lungs, it dissolves through the lining of your lungs. All right. Now, go for a bit of a rant here. So, the opioid crisis, Levitra, you know, Big Pharma is, in my opinion, and, you know, take it for what it's worth, Big Pharma's a blessing and a curse, because they provide us with all these drugs, but are they providing us the right drugs, right? You know, if we spend as much money as we spend on, you know, giving middle-aged men erections and hair, right? That's the main funding for drugs, is erections and hair, right? We probably have solved cancer by now, okay? So, you know, as organic chemists, you know, you come through and you think, oh, I'm going to change the world, I'm going to create the next, you know, well, the cure for cancer, and then you end up working for a company and you ended up on the Boner Pill project, okay? It's a bit like Bernadette from The Big Bang Theory, if you watch that show, because they talk about it, right? Okay, not just me. All right, so that's that. All right, now, the next topic, okay, the next topic, and I forgot to start my timer, all right. Next topic is solubility equilibrium. So, you know, when we have a solid dissolving in water. So what I'll actually do, I'll actually stop there because I'm not sure when I'm going to run out of time. And then we'll have one more video which has just the remaining few pages. Okay, so we'll stop there.